Lecture 13, Sensory Thresholds and Signal Detection. In the last lecture, we examined some of the modality-specific qualities of sensation, such as visual hue, color vision, and auditory pitch. This work illustrated the general psychophysical principle that every psychological property of a sensation is related to some physical property of the corresponding stimulus. In this lecture, we're going to look at one quality that all sensory modalities have in common, the quality of intensity, which is known as brightness in vision and loudness in audition. Sensory intensity, brightness and loudness, is also related to a physical property of the stimulus, which is its physical intensity, how strong the stimulus is. Just as each neuron has a threshold for firing, so each modality has a threshold for detection, the minimum amount of stimulus that's necessary for the person to have conscious awareness of the stimulus. And we can distinguish between two somewhat different kinds of thresholds. The absolute threshold is the weakest stimulus that can be detected in some modality. The human sensory apparatus is remarkably sensitive, especially for vision. Under optimal circumstances, we can detect a candle flame 30 miles away on a dark night. But we can also smell a single drop of perfume in a 6-room house. The relative threshold is the smallest change in intensity that can be detected, what's known as the just noticeable difference in stimulation. The absolute threshold is really a special case of the relative threshold, as it represents the just noticeable difference between sensing nothing and sensing something. In terms of psychophysical relations, the intensity of the sensory experience is related to the intensity of the physical stimulus that impinges on the sensory receptors, on the eyes or on the ears or whatever. That would seem fairly obvious. But in fact, there isn't a perfect isomorphism between the physical intensity of a stimulus and the intensity of the corresponding sensory experience. The actual psychophysical relationship between physical intensity and sensory intensity is a little bit more complicated than that. But let's step back for a moment and look at how the intensity of a stimulus is coded in the nervous system. There's a puzzle here because, as you remember, neurons operate according to an all or none principle. A neuron either fires or it doesn't, depending on whether it's crossed its own threshold for depolarization. But if neurons fire discretely, either they fire or they don't, how can we get continuously varying intensity encoded in the nervous system? The answer is found in two principles, temporal summation and spatial summation. In temporal summation, intensity is correlated with the frequency with which any particular neuron fires. More intense stimuli will produce more frequent firing. Less intense stimuli, less frequent firing. And this frequency of neural discharge is recorded in the nervous system. The other principle, spatial summation, has to do with the number of neurons that are firing at any particular time. Intense stimuli will activate a fairly large number of neurons. Less intense stimuli, a smaller number of neurons. So intensity is coded in the nervous system by the summation of activity in sensory neurons. Temporal summation in terms of the frequency with which any single unit discharges, and spatial summation in terms of the number of units that are active simultaneously. But now let's return to the problem of the intensity of sensory experience and how it's related to physical intensity. As I said earlier, it turns out that there's no isomorphism between physical and sensory intensity. For example, the relative threshold, or the amount of change in physical energy that's needed before that change can be detectable by the observer, depends on the intensity of the original stimulus. If the original intensity was low, even a very small change can be noticeable. If it's high, a relatively large change is required before it can be detected by an observer. This principle is represented in the earliest psychophysical law known as Weber's law, which is expressed mathematically as delta I over I equals C, where I is the physical intensity of the stimulus. And so delta I is the change in intensity, and C is a constant. In other words, the amount of intensity which must be added to a stimulus to produce a just noticeable difference is a constant fraction of the original intensity. So, to take an example, let's assume that Weber's fraction for some sensory modality is 1 over 10. C equals 1/10. So if the intensity of the original stimulus is 10 units, then a change in that stimulus is first noticeable at 11 units. If the intensity of the original stimulus is 100 units, then change is first noticeable at 110 units, not 101. And if the intensity of the original stimulus is 200 units, then change is first noticeable at 220 units, not 201 or even 210. The greater the intensity of the original stimulus, the more has to be added to that stimulus to make a change in intensity noticeable. Weber's fraction differs for each sensory modality and for each species, and so it provides a kind of universal index of the sensitivity of a modality. Thus, if some sensory modality is associated with a small Weber's fraction, it is highly sensitive. Even small differences are noticeable. If Weber's fraction is relatively large, it's not so sensitive. It takes a larger difference to be noticeable. In humans, vision is the most sensitive sensory modality, though we are also very sensitive to changes in heaviness and also changes in pain stimulation. The auditory modality is also pretty sensitive. Smell and taste much less so. But in cats, Weber's fraction for smell is about 1/300th that of humans. Cats are very, very sensitive to smells. A more general principle relating sensory intensity to physical intensity is known as Fechner's law, which is stated mathematically as S equals K times the log of I, where S is sensory intensity, experienced intensity, I is physical intensity, K is a constant, and log, of course, refers to a logarithmic function. Now, I want to reassure you that in this course we're not going to hold you responsible for the specifics of a law like this, but I want you to get the idea of how these psychophysical laws work, because they illustrate some important general principles. Fechner's law says that for every value of I, for every value of physical intensity, there's a corresponding value of S for sensory intensity that is given by the formula. So ignore the constant K for purposes of illustration and assume that we're dealing with logarithms to the base 10. If the physical intensity of the stimulus is 1 unit, then the sensory intensity is 0 units. Log to the base 10 of 1 equals 0. If the physical intensity is 10 units, then the sensory intensity is 1 unit. Log to the base 10 of 10 equals 1. If the physical intensity of the stimulus is 100 units, then the sensory intensity is 2 units. Log to the base 10 of 100 equals 2. And if the physical intensity is 200 units, then the sensory intensity is 2.3 units. Log to the base 10 of 200 equals 2.3. Here's what's important. According to Fechner's law, sensation changes more slowly than stimulation. In the examples I've given, physical intensity has grown from 1 unit to 200 units, but sensory intensity has only gone from 0 to only 2.3 units. This actually follows from Weber's law. 10 additional units of stimulation make a big difference to sensation at the bottom end of the scale, but a progressively smaller difference as we move towards the top. Sensation changes more slowly than stimulation, And that's the important principle. Just as an aside, if you plot the physical intensity of the stimulus on a logarithmic scale, you get a perfectly straight line expressing Fechner's law. The 19th century psychophysicists loved this because straight lines seemed to indicate to them that they really had uncovered a fundamental psychological law with their mathematics. Fechner's law, that sensation changes more slowly than stimulation, holds true across a wide range of stimuli, but there are some exceptions. For example, within wide limits, the perceived length of a line changes precisely with the actual length of the line. And, typically, experienced pain grows more rapidly than the pain stimulus. If you don't believe this, the next time you're at the dentist having a cavity filled, just ask him to press down a little bit more. To accommodate these kinds of empirical findings, we have an even more general psychophysical law known as Stephen's law, which handles all the cases that follow Fechner's law plus the exceptions. In fact, Stephen's law is so general that it handles all known psychophysical relations. Stephen's law states mathematically that S equals K times I raised to the nth power, where, again, S equals sensory intensity, I equals physical intensity, K is a constant, and N is an exponent, either a power or a root. In other words, Stephen's law states that for any quality of sensation, there is some exponent that relates changes in sensation to changes in physical stimulation. Here's how it works for the general case, the cases that are covered by Fechner's law. Fechner's law is a special case of Stephen's law where the exponent n is less than 1. An exponent of 1/2 means the square root of a number. An exponent of 1/3 means the cube root, and so on. So let's just consider what happens when n equals 1/2, or 0.5. If the physical intensity is 1 unit, then the sensory intensity is also 1 unit, because the square root of 1 equals 1. If the physical intensity is 10 units, then the sensory intensity is 3.16 units, because the square root of 10 equals 3.16. If the physical intensity is 100 units, then the sensory intensity is 10 units. The square root of 100 equals 10. And if the physical intensity is 200 units, then the sensory intensity is 14.14 units, because that's the square root of 200. Although the precise values differ from those that I gave in the illustration of Fechner's law, because Stephen's law is a different mathematical formula, notice that the outcome is the same. Big changes in I yield relatively small changes in S, just as predicted by Fechner. As physical intensity grows from 1 to 200 units, sensory intensity grows from 1 to only about 14 units. When n, the exponent, equals 1, you get the first exception to Fechner's law, like the length of a line, where every change in I, physical intensity, corresponds to a precisely isomorphic change in S, or sensory intensity. And where n, the exponent, is greater than 1, you get the other exception to Fechner's law, of which pain is an example. So, for example, assume that the exponent for pain is 3/2, or 1.5, the square root of the cube of I. If the physical intensity is 1 unit, then the sensory intensity is also 1 unit, because the square root of the cube of 1 is still just 1. But if the physical intensity is 10 units, then the sensory intensity is 31.6 units. 10 raised to the 3/2 power equals 31.6. And if the physical intensity is 100 units, then the sensory intensity is 1,000 units, because 100 raised to the 3/2 power is 1,000. If the physical intensity is 200 units, then the sensory intensity is 2,828 units, because that's what 200 raised to the 3/2 power comes out to be. Notice, again, that physical intensity grew from 1 to 200 units, but sensory intensity grew from 1 to almost 3,000 units. Even a small change in I produces a big change in S when it comes to something like pain. In a very real sense, Stephen's law is a general psychophysical law that applies to all modalities and all qualities within a modality. There's always some exponent that relates the physical quality of the stimulus to the psychological quality of the resulting sensory experience. And the goal of psychophysical research is to determine what that exponent is. So, Stephen's law, in some sense, describes the operating characteristic of the sensory transducers, operating characteristic being a term that was brought over from engineering. Most sensory receptor systems compress stimulation, thus following Fechner's law, and Stephen's law where the exponent is less than 1. When some sensory systems, such as pain, expand stimulation, that can't be accounted for by Fechner's law, but is accounted for by Stephen's law when the exponent equals a value greater than 1. In one of his papers, Stevens reported a whole bunch of different exponents for different psychophysical judgments. And no, you don't have to memorize these. The early psychophysical laws were great advances on the way towards a scientific psychology, and Stephen's law is another great advance. But after Stevens articulated his law, there evolved a gradual appreciation that the psychophysical laws, even Stephen's law, were somewhat misleading. One troublesome aspect of all the psychophysical laws was that they were derived from somewhat sterile laboratory conditions, in which there were no special rewards for detecting a stimulus and no special costs for missing one, or for detecting a stimulus, if you will, that wasn't actually there. And that's really not characteristic of sensory detection in the real world, where, at times at least, detection accuracy can literally make the difference between life and death. Consider, for example, a soldier on guard duty. If there are reports of the enemy in the area, he or she is going to be especially alert and responsive to any unusual noise, and in fact may fire at somebody who is not in fact an enemy. But if there are reports of no enemy in the area, he or she may slack off somewhat and miss the vanguard of an invading enemy force. The psychophysical laws don't really take into account these kinds of considerations. Accordingly, a new approach to psychophysics began to develop in the 1960s known as signal detection theory, which tries to understand how observers in the real world detect signals, or detect changes in stimulation. Signal detection theory assumes that all stimulation occurs against a background of noise, and the observer's task is to discriminate between the signal and the noise. Or, put another way, to determine when there's a signal in a background of noise. Whereas classical psychophysics assumed that this was simply a matter of the intensity of a signal against the background intensity of the noise, signal detection theory understood that the analysis of detection needed to take both motivation and expectancy into account, whether the person expects the signal to be there or not, and what the costs and benefits are for detecting the signal or missing it. In the end, signal detection theory produces not just a measure of the sensitivity of some sensory system, but also some measure of the criterion that the observer uses to decide whether a signal is present or not, a criterion that can be biased either by the observer's expectations or by the observer's motives. The measurement of sensory sensitivity is often given in terms of a statistic known as D prime, whereas the measurement of bias, or the observer's criterion, is often given in terms of a measurement known as beta. As with most other statistical formulas in this course, you don't have to worry about the calculation of d prime and beta. You'll see how it works in a couple of minutes. But I do want you to be able to recognize these terms, d prime as a measure of sensitivity in signal detection theory, and beta as a measure of bias, or the observer's criterion. In the basic signal detection experiment, a stimulus or signal is presented against a background of noise. Some trials present both signal and noise. That's where the signal is on. Others present just noise. That's when the signal's off. These are sometimes known as catch trials. And the task of the subject is to say on each trial yes or no whether the signal is present. The task is made fairly difficult by the fact that the signal is just slightly more intense than the noise. And that's a situation that injects considerable uncertainty into each trial. When a signal is actually present and the subject says yes, that's a hit. When it's present but the subject says no, that's a miss. When the signal is actually absent on what is known as a catch trial, but the subject says yes anyway, says the signal is present, that's known as a false alarm. And when the signal is off and the subject says no, there's no signal, that's called a correct rejection. Signal detection experiments focus mostly on hits and false alarms. So now imagine a situation in which we've got a very sensitive observer and the experiment has 50% catch trials. 50% of the trials the stimulus is on, 50% of the trials the stimulus is off, and there's just noise. A highly sensitive observer would make no mistakes. He or she would say yes, the signal is on 50% of the time, and on every one of those trials he'd be right. The stimulus was actually on. This corresponds to a 100% hit rate. Every time the stimulus is on, the person says yes. But there's also a 0% false alarm rate. Every time the stimulus is off, the person says no, there was no signal. So that yields 100% hits, no misses, 0% false alarms. The calculations of signal detection theory would yield a high value for d prime, indicating that this observer is highly sensitive to the presence of the stimulus, and a value of 0 for beta, the measure of bias, indicating that the person has neither a conservative bias to say no or a liberal bias to say yes. Now let's look at the same experimental setup, but a slightly different level of performance. Again, 50% of the trials the stimulus is actually on. 50% of the trials the stimulus is off. There's just noise on the catch trials. This time the observer says yes, the stimulus is on only 40% of the time. And he's right every time. Every time he says yes, the stimulus is on, the stimulus is actually on. But he also misses some signals. Values like this correspond to an 80% hit rate. 40% is 80% of 50%, and a 20% miss rate. 10% is 20% of 50%. But he still doesn't make any false alarms. His false alarm rate is 0%. When he says yes, the stimulus is on. He never makes that mistake. With outcomes like this, the formulas of signal detection theory indicate that, indeed, this observer does have somewhat lower sensitivity than the one we discussed in the previous slide, but it's still pretty good. But this time the formulas indicate that there's a little bit of a response bias, a conservative response bias. He never says that the stimulus is on when in fact it's off, so he's behaving very conservatively. He's set a very high criterion for saying yes. Here's an example of a subject with absolutely no sensitivity, but a very liberal response bias. He's set a very low criterion for saying yes. Again, 50% of the trials are catch trials. On 50% of the trials, the stimulus is on, and on 50% of the trials, the stimulus is off. But this subject says, yes, the stimulus is on 80% of the time. Sometimes he's right. He's got an 80% hit rate, just like the previous subject did. But often he's wrong. He's also got an 80% false alarm rate. He says that the stimulus is on 80% of the catch trials. In a situation like this, where the hit rate equals the false alarm rate, the formulas of signal detection theory indicate that this observer has no sensitivity at all. He's not really detecting any signals. He's really just guessing. But he's got a very low criterion for saying yes. He's got a liberal bias towards saying yes. Here's another subject who's also just guessing, but who's using a very different response strategy. He's saying no to almost everything. He says yes, the stimulus is on only 30% of the time. He's right sometimes just by chance, but he's also wrong an equal number of times, so that he misses more than he hits when the stimulus is on, which ordinarily would indicate that he's simply got very low sensitivity. But his hit rate of 30% is equal to his false alarm rate of 30%, because it hits equal false alarms. The formulas of signal detection theory indicate that this person also has absolutely no sensitivity, but they also reveal that this observer has a bias towards saying no, a very conservative bias against saying yes. Here's a somewhat more realistic example of an observer who has some sensitivity to the signals, actually does detect some signals, but also has a liberal bias towards saying yes. Here we have the same hit rate as in an earlier example, 80%, but now we have some false alarms too, a false alarm rate of 40%. Because the hit rate is greater than the false alarm rate, you can see that this individual does have some sensitivity. He's actually detecting some signals. But with a false alarm rate this high, we can also say that this individual has a somewhat low criterion for saying yes. This low criterion for saying yes leads him to say yes even when the stimulus is actually off on some occasions, leading to a relatively high false alarm rate. And here's another example of a subject who's got some sensitivity to the stimulus, but also a very conservative response bias, a very high criterion for saying yes. Here the subject says yes only 30% of the time, but most of these times the stimulus is actually on. So he's got a 50% hit rate, but he missed a lot of the stimuli. The important thing, however, is that he doesn't make very many false alarms. He's only got a 10% false alarm rate. Under these circumstances, the formulas of signal detection theory will indicate that this person has relatively low sensitivity, but he does have some genuine sensitivity to the stimulus. He's just biased against saying yes. He has a very conservative response bias towards saying no. Now, in all of the previous examples, the stimulus has been on 50% of the time and off 50% of the time. 50% of the trials have been catch trials. Within the signal detection framework, we can manipulate the observer's expectations by varying the proportion of catch trials, trials in which the signal is actually off. Here we have a situation where the stimulus is actually presented 70% of the time, and only 30% of the trials are catch trials. And here's a subject who has considerable sensitivity to the presence of the signal. The hit rate is greater than the false alarm rate. Here we have a 74% hit rate and a 60% false alarm rate. But it's also clear that the relatively low number of catch trials has induced a liberal bias towards saying yes, which results in the relatively large proportion of false alarms. This kind of outcome, applying the formulas of signal detection theory, would indicate some sensitivity, but also pick up on the liberal response bias. And here's an example where the situation is just the reverse. Now we've got 70% catch trials and only 30% trials where the stimulus is really on. The subject picks up on this, so he now has become very conservative in his responding, saying yes on only 30% of the trials. He's right more often than he's wrong, so he has a hit rate of 60% and a false alarm rate of only 17%. The fact that hits are greater than false alarms means that this individual does have sensitivity to the presence of the stimulus. But there's also a very conservative response bias here. He's got a very high threshold for saying yes, with the result that he misses a lot of the times the stimulus is on. In addition, in signal detection theory, we can manipulate the observer's motivations by means of a payoff, the consequences for saying yes or no, or for being right or wrong. Here's a balanced payoff matrix in which the observer earns 25 cents for every hit and loses 25 cents for every false alarm. He also loses 25 cents for every miss, and he gets 25 cents every time he makes a correct rejection. So, when he's right, he gets a quarter, and when he's wrong, he loses a quarter. Here's a payoff matrix that will induce a liberal response bias on the part of subjects. Here, the observer gets a quarter for every hit, but loses only a dime for every false alarm, and doesn't get anything or lose anything for a miss. Under these circumstances, a rational subject will tend to say yes. He'll be right more often than he's wrong. When he's right, he'll earn more than he'll lose when he's wrong. And it will all work out to a net gain. And the opposite payoff matrix is pretty much guaranteed to induce a conservative response bias. Here, the observer earns a dime for every hit, but loses a quarter for every false alarm. So the net expectancy for saying yes is a loss of 15 cents. Under those circumstances, you're not going to say yes unless you're really certain that a signal was present. There are lots of other ways to induce conservative or liberal biases, and you can imagine combinations that vary both the payoff matrix and the base rates. But I think you've probably had enough of signal detection theory now to get the idea behind it, so let's move on to a summary. Signal detection theory offers a general model for decision-making under conditions of uncertainty, that is, where the distinction between signal and noise is relatively difficult to make. And we'll see other applications of this general framework later on in the course. For example, consider an oncologist who's examining an X-ray or a CT scan for signs of cancer, signs of a tumor. There may be a tumor visible in the scan, but this signal is going to be embedded against a background of noise created by the surrounding tissue. If the patient has a family history of cancer, the physician may expect to find a tumor in this patient as well. Or he may see a tumor even if a tumor really isn't there. That is, make a false positive. Of course, seeing a tumor that's not there has some cost attached to it, in terms of further exploratory surgery that may be warranted. But if the surgery outcome is negative, that is, they don't find evidence of a tumor, the cost of that decision may be much less than that of missing a tumor that really is there. So in looking for signs of cancer, the oncologist is trying to detect a signal against a background of noise. This is a decision that will be influenced both by the physician's expectations of whether there might be a tumor there or not, and by the costs and benefits of whatever decision he or she makes. For now, we can simply say that signal detection theory has a number of important implications for the study of sensation. In the first place, it makes it clear that detecting a signal is not simply a matter of the intensity of that signal, the physical intensity, as the earlier psychophysical laws seem to imply. Moreover, signal detection theory seems to deny that there is such a thing as absolute sensitivity. The sensitivity of an observer to a signal is going to vary with the expectations and motives of that observer. Classical psychophysics seems to have been formulated under something very close to a view of the observer as a passive receiver of stimulation. If the stimulus were intense enough, the observer would detect it. If the change were big enough, the observer would detect it, and that's all there is to it. But, as with the doctrine of the passive organism that we encountered in our discussion of learning theory, the doctrine of the passive observer seems not to be right here either. Rather, the observer, the signal detector, is active throughout the process. The proximal stimulus is transduced and transmitted through the nervous system just as a matter of physiology. But in the final analysis, the observer has to make a judgment about whether the stimulus is present or whether it's changed. These decisions are going to be heavily influenced by the observer's expectations, by what he believes to be the likeliest case, and also by his motives, by his understanding of the payoffs, rewards, and punishments. Finally, signal detection theory tends to undercut the traditional distinction between so-called lower and higher mental processes. The early psychologists made this distinction between lower and higher mental processes depending on how close to the stimulus the observer's mental state was. Sensation and perception were regarded as lower because they were very close to the stimulus and very close to the physiology of the sensory system. Memory and reasoning and problem-solving were characterized as higher because they were not so closely tied to the physical stimulus and sensory physiology. But signal detection theory makes it clear that even at the very lowest level of mental life, just at the level of detecting a stimulus or detecting a change in a stimulus, that's a decision. That's a judgment that's influenced by the person's goals and expectations. Signal detection theory makes it clear, at the very least, that the operation of so-called lower mental processes can be critically affected by the operation of so-called higher mental processes. In fact, I think it breaks down this distinction entirely, and I don't tend to refer to it at all. I don't make a distinction between lower and higher mental processes in this way. But we'll see more examples of how so-called higher mental processes of reasoning, judgment, decision-making, learning, and memory affect so-called lower mental processes when we come to the phenomena of perception, which is where we're going to turn our attention next. If there's really no such thing as absolute sensitivity, one begins to wonder whether there's such a thing as an absolute threshold. The whole idea of a sensory threshold, based on the analogy of a neuron's threshold, comes to us from Herbart, a philosopher and physiologist in the 19th century who, writing in German, actually used the term Lyman for what we call, in English, threshold. And almost immediately, psychologists began to wonder if there were such a thing as subliminal perception, that is, perception of a stimulus that is below the threshold for conscious detection or conscious sensation. The question of subliminal perception is whether there are circumstances under which a distal stimulus can have palpable influence on the observer's experience, thought, or action, even though the observer is not consciously aware of that stimulus. There's no conscious perception, but perception is implied by the observer's performance on some task. To give you an example of what I'm talking about, here is the data from the very earliest experiment on subliminal perception. In fact, this is the first psychological experiment ever published by American researchers in an American scientific journal. It was performed by the philosopher C.S. Peirce and his graduate student Joseph Jastrow and published in 1884. Jastrow later went on to become a very famous psychologist. Peirce and Jastrow wanted to put the concept of the threshold for sensation to a rigorous test. They weren't sure that there were such things as sensory thresholds. They actually worked on difference thresholds but you can get the idea about what their study would have looked like if it had focused on absolute thresholds. Peirce and Jastrow presented their observers with two weights in one experiment, one just a little bit heavier than the other. In another experiment, they used two lights, one just a little bit brighter than the other. But this is the data from the weight experiment. And the observer's task was simply to say whether there was a difference between the two stimuli. So again, this has to do with relative thresholds. In addition to asking their observers to make their judgment, they also had observers rate how confident they were in the judgments they were making. When the ratio between the weights was relatively large, the observers were both highly accurate and highly confident. But as the ratio was progressively diminished, the subjects became less accurate and less confident. Finally, the ratio between the two weights was so small that the observers were at zero confidence. They could no longer consciously distinguish between them, and they experienced themselves as simply guessing. Nevertheless, as this graph shows, these observers were more accurate than you'd expect by chance. If they were really guessing, they'd be right 50% of the time. But even at the lowest ratio between the two weights, the observers were right about 60% of the time. This looks like a small difference from 50%, but that's why we have statistics. It's actually a big difference statistically. And, interestingly, back in the 19th century, Peirce and Jastrow had to invent some statistics much like the ones we now use, in order to make the case that 60% really was significantly better than chance. So here we have an apparent example of subliminal perception. There is no conscious perception. The observers really don't have any confidence in the judgments that they're making. They don't consciously detect any difference between the two weights. But forced to guess, they choose the correct answer more than 50% of the time, about 60% of the time. That effect on guessing behavior is an index of subliminal perception. The fact that the subject's guesses are accurate more often than we'd expect by chance, even though they have zero confidence in their judgments, provides evidence that the stimulus was in fact detected at some unconscious level. There is some perceptual processing of the stimulus, or the difference between these two stimuli, that's occurring outside of awareness. Since the experiments of Peirce and Jastrow, and especially since the 1980s, evidence favoring the concept of subliminal perception has mounted. It's still controversial in some quarters, but most everybody is now convinced that subliminal perception can be dissociated from conscious perception, and there can be perceptual processing of stimuli of which the perceiver is not consciously aware. In the earlier studies, the stimuli in question were truly subliminal. They were very, very, very weak stimuli, or very, very small differences between stimuli, as in the case of the Peirce and Jastrow experiment. They were too weak to be consciously detected. Later on, stimuli were presented that were too brief to be consciously detected. And still later, experiments employed what are known as masking procedures, which render the critical stimulus essentially invisible, not consciously detectable. There are also experiments in which subjects' behavior is affected by suprathreshold stimuli that are above the sensory threshold but presented outside the scope of their conscious attention, so-called unattended stimuli. In each of these cases, we can distinguish subliminal perception from simple guessing using the kind of logic that's associated with signal detection theory. In experiments like those of Peirce and Jastrow, and in related experiments like the ones that we do today, the hit rate is greater than the false alarm rate. There is some sensitivity to the stimulus there, even though the subjects are not consciously aware of the stimulus. That shows that they're doing something other than mere guessing, even though what they're responding to is something that they're not consciously aware of. At the same time, it's important to point out that there are limitations to so-called subliminal perception. For example, sometimes you see claims for the effectiveness of subliminal advertising, where somebody will put a brief ad for a soft drink on a movie screen and people will run out to the concession stand and buy that item. These claims are, so far as we can tell, grossly exaggerated. Subliminal perception occurs, but subliminal perception is analytically limited. It's not nearly as powerful. It doesn't have nearly the effects on experience, thought, and action as conscious perception does. Subliminal perception is interesting from a theoretical point of view in terms of what it tells us about how perception works and the relation between conscious and unconscious mental life. But it doesn't really work as a means of influencing people, altering their behavior outside of conscious awareness.